Good morning, everybody. It is Monday morning, the 1st of October. Hard to believe it's October already. Anyway, I'm going to do a pre-lecture for our Tuesday's class, and I am not feeling particularly well this morning, so hopefully I can make it through this in a coherent fashion. So we're going to be looking at section 13.4. This is the last section of chapter 13 that we're going to cover. I think we've pretty much covered the whole chapter. We did skip this one at the time because I wanted to focus on the rate law. So remember, the general form of the rate law, if we just have one reactant A going to products, is rate is equal to the rate constant times the concentration of the reactant, and we only have one reactant here, to some power. And that power, that exponent, we call the order of the reaction. So typical orders are first, second, and even zero order. And those are the ones we're going to focus on for today. So again, make sure you realize what this tells us. This tells us how a change in concentration impacts the rate of the reaction. So typical reactions, you increase concentration, rate increases. Other direction, decrease concentration, rate decreases. Now, zero order is a special case where rate is constant, and we'll get to that later. So we're going to actually turn the table here and look at something different, because what we know is for a typical reaction, say first or second order, if we're looking at how the concentration changes over time, and we've talked about this a little bit, looking at a first order reaction, so if X is equal to 1, okay, as the reactant reacts, the rate slows down because the concentration is decreasing. And so the concentration drops off in a fashion like this. Okay. So what we want to develop here is we want to be able to develop an equation where we can calculate the concentration at any time later in the reaction. So we start out with some initial concentration, but what is the concentration at this time? Or what is the concentration at this time? And that's the equation we're going to develop, and that's called the integrated rate law. Okay, so let's just get to that. Make sure I'm not forgetting anything here before we move on. If I am, I can come back to it, I guess. Okay, so let's start with first order. And we're going to look at first, second, and zero order. So let's look at a first order reaction. So we know two things about a first order reaction. And we're only focusing on one reactant. So we have that equation. But we also know that in general, rate is the change in concentration, in this case one reactant A, over the change in time. Okay, so that's just the definition of rate, change in concentration with time. So these two equations both equal the rate of the reaction. So we can set those equal to each other. So we can write delta A over delta T. And remember, it has a negative sign because the reactant concentration decreases as the reaction runs. So again, this is first order. Now, we can rearrange this and get the concentration terms on one side and the time term on the other. So I'm going to multiply through by delta T. I'm also going to divide by concentration of A, and I end up with this equation here. Okay, so for those of you who have taken calculus, you might have, and I think I remember from college, we didn't do integrals until Calc 2, but I'm not sure how they teach it here. But we're going to integrate this equation. Now, typically, when you're doing calculus type things, you use a d instead of a delta, so it'd be dA over A and kdt. If you haven't taken calculus yet, don't worry. I'm just going to explain what we're doing for those who know how to integrate. We're going to integrate this side of the equation from the concentration at time 0, so a subscript 0 at the start of the reaction, to the concentration at some later time. And then we're going to integrate this side of the equation from time 0 up to some later time t. And if you do that, what you end up with, well, we get two different forms of the equation, but let me write both of these. One form of the equation is this one, natural log, and this is rearranged. So if you're trying to do this, I've already rearranged the equation. You end up with the natural log of the concentration at some later time t is equal to minus kT plus natural log of the initial concentration at time 0. Okay, so this is what we would call the integrated first order rate law. Okay. Now I will give you this reaction. You don't have to memorize it, but you do need to know that this is the first order integrated rate law. And it's easy to tell it has a natural log term in it. We'll see the other ones have a different form than this, whether it's second order or zero order. All right. The nice thing about this equation, we're going to come back to this, is that this form of the integrated first order rate law has the form of a straight line, okay, where your y value is natural log of the concentration, your x value is time, this is your y-intercept, and your slope is negative the rate constant. So if you look on page 575, you will see a problem, an example 13.3. So you should take a look at this, where you're given data, time and concentration, and then we can plot that. Okay, we can plot natural log of concentration versus time, because that's our y value. So if you look at the plot there, natural log of concentration. Now they have a particular reactant, but let's just say, just in general, whatever the reactant is, versus time. And if it's first order, okay, remember, because this is the first order integrated rate law here. Okay, if the reaction's first order, you should get a straight line. Okay, so look at page 575, and they've actually plotted the data. And then what else do we? So one thing that would tell us is that if you do get a straight line making this plot, natural log of the concentration versus time, it would tell you that it's first order. So that's one way to confirm the order of reaction. The other thing that it allows you to do is look at what the slope is equal to. The slope is equal to the negative of the rate constant. Okay? So this is actually a very powerful equation in this form. Linear equation. We can confirm a first order reaction if we get a straight line plot, and we can also calculate the rate constant from the slope. So if you look at the problem, they show you the slope. You do get a negative slope because the slope is a negative of the rate constant. Rate constants are positive. So when you take the negative of a negative slope, you're going to get a positive rate constant. Okay. So read through that and then go over to the next page. Let me show you, and I'm going to turn my page here. Let me show you another form of this equation. This is still the integrated first order rate law. Natural log of the concentration at time t over the concentration at time 0 is equal to minus kt. That's just rearranging the previous equation. But sometimes this form is nicer. It's not linear as it's written. But a lot of times it's easier to solve for time if you have it in this form. So depending on what you're solving for, might make your life easier to use this equation. And I will give you both of those. Both of those are integrated first order rate laws. Okay, so take a look at example 13.4 on page 576. And in this one, you're actually plugging into this equation. They're actually using the linear form of the equation. Again, you could use either one. Okay. Now we'll work some of these problems in class tomorrow, but I would like you to take a look through this problem where they're actually giving you the rate constant, which they calculated in the previous example. You have a concentration, and it says what is the concentration at a later time. Okay. So remember, this T means the concentration at later time. This is the initial concentration at time 0, and T is time, and K is your rate constant. Okay, so it's just plug in and solve. All right. Now, for sake of time, and since I've already gone 9 minutes, I'm just going to go through and write out the second and 0 order rate laws, rather than going through how we're rearranging and setting those up. But you do them in the same fashion. It's just that if you were doing this for the second order, you would say rate is equal to Ka squared, and you would also say rate is equal to the change in concentration of reactant A over change in time. And you would set those two equal to each other. You would integrate both sides of the equation, and you would come up with this second order integrated rate law. And it looks like this. 1 over the concentration at a later time is equal to, now this has a positive slope, Kt plus 1 over the initial concentration. Okay, so this is the second order integrated rate law. Okay, easy to distinguish from the first order because the first order integrated rate law has a natural log term. This has a 1 over concentration term. Okay, but the same thing, as you might see already, this has the form of a straight line, y equals mx plus b. So we can make a plot of 1 over the concentration. That's our y value. Our x value is time. Now this has a positive slope, so if it's a second order reaction, we should get a straight line. Slope is equal to the rate constant. And again, that's if the reaction is second order. So again, this is one way to confirm if a reaction is second order. You could collect data, concentration, time, plot 1 over concentration versus time. If you get a straight line, boom, it's a second order reaction. And then you can also calculate the rate constant directly from the slope. So example 13.5 goes through a problem where it's, again, doing concentration and time data, making two plots. So they're showing here, is it first or second order? So that's what this problem is looking at. Is it first or second order? Okay, so there's actually two plots done here. There's the natural log of concentration versus time plot. That would be first order. And there's 1 over concentration versus time. So take a look at page 577 and look at the two plots. One of them is a straight line. The other is not. Okay, because a reaction can't be both orders. It can't be first and second. It's going to be, well, those are kind of our typical orders. But in this case, the first order plot, natural log of concentration versus time, is not a straight line. But the second order plot is. 1 over concentration versus time is a straight line. So that shows that this reaction is second order, because you get a straight line for a plot of 1 over the concentration versus time. Okay, and then from that plot, we can get the rate constant from the slope. Okay, lots of stuff. And for sake of time, as I've said a couple of times, if you have a 0th order reaction, you end up with this equation. Okay, and this is also linear. Now this one has the simplest form, and it's because the rate of a 0 order reaction is constant. So if you take a 0 order and you go k a to the 0th power, a to the 0th power is just 1, and you get rate is equal to a constant. So if we plot, and I'm going to, hopefully I won't mess you up too bad here. If we plot concentration versus time, so go back and look at the initial one where it's not linear for a first or second order concentration versus time, because the reaction slows down as reactant is consumed. But for 0 order, rate is constant, and so this plot is actually a straight line plot, concentration versus time, which is what we see here, concentration versus time. Okay, so go back to the very first thing I started with, saying that the concentration doesn't fall off linearly with time for first or second order. For a 0 order, it does. So if you make a plot, again, of y versus x, concentration versus time, and you get a straight line, that would tell you it's 0 order, and the slope is equal to the negative of the rate constant, so a negative slope. So those are the 3 integrated rate laws that you need to know. Okay, and I don't think that your book goes through a problem other than to show you the plot that I just showed you, concentration versus time. If it's straight line, it's 0 order. Okay, the last thing I'm going to talk about, I'm at 14 minutes, is something called a half-life. So by definition, and looking at page 578, take a look at the definition of a half-life. And you've probably heard the term half-life, particularly in regards to radioactive substances. So the half-life is the time required for the concentration of reactant to fall to 1/2 of its original value. Okay, makes sense. Half-life. The time it takes to go to the reactant concentration to drop to 1/2 of its initial value. Now we can talk about subsequent half-lives too. So you could, cut the concentration in half. That would be the first half-life. Cut the concentration in half again. That would be the second half-life. Cut the concentration in half again. That would be the third half-life. So what we're going to look at here is the half-life equations for both a first and second order reaction. And so what we're going to start here is we're going to start with our integrated rate law that has this form. Well, actually, we're starting with first order. Let's do first order first, and then we'll do second order. Okay, so this is just the rearranged version of the integrated first order rate law. And at T1/2, which is the half-life, we know that the concentration, I want to put equal there, but at the half-life, the concentration at a later time is equal to half of the initial. Okay, that's what, by definition, what a half-life is. The concentration drops to half of its initial value. Remember, the 0 means time 0, so that's its initial concentration. So now we can take this and plug in for the concentration at a later time. We end up with, make sure I don't mess this up here, okay. Something doesn't look right here because I think we're supposed to end up with natural log of 2. So what did I do wrong here? Okay, sorry about that. I kind of confused myself, but this is correct. Again, I'm not thinking particularly clearly this morning. I definitely woke up and it seems like I have a little bug this morning. So what we end up with is the concentration at time 0 cancels out. We're left with a natural log of 1/2. Okay, is equal to minus kT. Take the natural log of 1/2, you get minus negative 0.693 is equal to minus kT. And actually this should be T1/2 because this is, by definition, half-life when the concentration is half its initial value. Multiply through by -1, these both become positive, and T1/2 is equal to 0.693 divided by K. All right. This is for first order. So this is the equation for a first order half-life. One thing we can use this equation for is to solve for the rate constant. So if you know the half-life of the reaction, you can solve for the rate constant directly. So all you have to do is look at the reaction when the concentration drops to half of its initial value. That's the half-life. Plug in that time, solve for the rate constant. Nice, easy way to solve for the rate constant. Now the example 13.6 actually does the opposite of what I just talked about. Page 579, so take a look at that. They actually give you the rate constant, solve for the half-life. Okay, so either direction. So we can either solve for one of the two things in the equation. Okay, and if we do the same thing for a second order, I will give you this half-life equation as well. We can perform the same type of manipulation, just plugging into the second order integrated rate law. And you might want to look at page 580 to see how that's done. But for a second order, we end up with a half-life equation equal to this. Okay, so this is the second order half-life equation. I will give you that as well. Now, the first order one is I think very interesting because you don't even see concentration in this equation at all. So what that means is each half-life is the same length for first order. So to go, say, from 1 molar to 0.5 molar is going to take a certain amount of time. All right. The second half-life, to go from 0.5 molar to 0.25 molar, okay, again, cutting that concentration in half, is going to be the same amount of time for a first-order reaction. The third half-life, to go from 0.25 to 0.125, is going to be the same time for a first order. So if you have a first-order reaction, each successive half-life for that particular reaction takes the same amount of time. For a second order, that is not the case because the concentration is in the equation. And so as your concentration gets smaller as the reaction runs, we are dividing by a smaller number, which means the half-life is actually going to get longer. So each successive half-life for a second order reaction is going to be longer, okay, because concentration shows up in the equation. Okay, I'm at 19 minutes. I think that's enough. Take a look at page 581. It summarizes a lot of what we've talked about today. It goes through it. It's a table 13.2 would be a good one to look at. And this is on page 581. And you'll see for 0, first, and second order, it shows you the rate law. It shows you the integrated rate law. It shows you what plot would confirm the order. Okay, so you need to know that. For zero order, it's concentration versus time. First order, natural log of concentration versus time. Second order, 1 over concentration versus time. And then it goes through and shows the half-life expressions for those. Okay, and so I didn't solve for the zero order one. You can look at that. That's also on page 580. Okay, I will give you all these equations. But you do need to know, I'm not going to tell you, oh, this is a zero order one, this is the first order one, this is a second order one. But they're pretty easy to tell apart. Okay, I will see you in class tomorrow. Take care.